Hello everyone, welcome to Fluid Mechanics Recitation for week 11. This week we have 10 questions and they are mostly relevant to turbine and power questions. So in the first question, we have a system with reservoirs and turbine. So the discharge is 480 cubic feet per second. And what is the power output from the turbine? And we are assuming an efficiency of 85%. And overhead loss is 1.3 V square per 2G. And V is the velocity in this 7 feet penstock, like this pipe. And we are assuming a constant coefficient. So we need to find power output. So to find the power output, we need to find the head for the turbine. So let's say this is 0.1 and this is 2. So let me write energy equation. So we have everything same, like in these terms. And additionally, we have pump, we have turbine, and we have head loss. And we usually select water reservoir surfaces because if you do that, we can directly ignore pressure, velocity for both sides. So it will make our calculations easier. So this is 0, this is 0, this is 0, and this is 0. And the main reason for that, as you are already familiar, we have a reservoir open to the atmosphere in both tanks. And since they are at the surface, the velocity is very small so that we can neglect. So let's continue with the current terms. And we also don't have pump here. So we have Z1, which is the elevation of 0.1, equal to Z2 plus turbine's head and the head loss. So here, the head loss is given as 1.3 V square over 2G. And we need to find HT because we can find the power output. So Z1 minus Z2 is also known. So Z1 is 35, which comes from here. And we can assume this is the point 0, so it will be 0. Plus HT plus head loss. So here the only unknown is V. And I mean, it is V and HT. So we can actually get HT, we can get velocity from the given discharge so that we can find HT. So Q is 480 cubic feet per second. And the area is pi 7 feet square over 4. So from here, let me write like this. So from here, velocity is 12.47 feet per second. So we also have V square over 2G. So it will be 12.47 square over 2 times 32 0.2 feet per square second. So this gives 2.416 feet. And from here, we have 35 equal to HD plus 1.3 times 2416 feet. And from here, HD will be 31.86 feet. So this is the water head, which is provided by turbine. So to find the power output from turbine, we need to use this. And we usually calculate it in horsepower or megawatts. So let's continue with horsepower, then we can convert to megawatt. So similar to what we do in calculating power of pump, we have flow rate, we have specific rate, we have head, and we have efficiency on top. And actually, let me continue with this first, then we can convert to horsepower. So we have 480 cubic feet per second times 62.4 times the head. And let me move this a little bit. And we have efficiency. So this is going to give 8,111.30 pound force times feet per second. So we have this relationship between pound force times feet per second. So 1 horsepower is equal to 550 pound force times feet per second. So in terms of horsepower, we will get right in this one. We'll get 1470 horsepower, and this is going to be equal to 1.10 megawatt, because we have another relationship between the horsepower and megawatt. And let me write it quickly. So using this relationship, we can calculate the horsepower in megawatts. And since this power equation gives 800,000 pound force times feet per second, we can convert this to HP, which is horsepower. So 1 horsepower is 550. So we will have 1,470 horsepower. And using this equation, we will get 1.10 megawatts. This is second question, 7.51. Here we have a pump, and it draws water through a 20 centimeter suction pipe, and then it discharges it through a 11 centimeter pipe. So it is sucked by this pipe, then the diameter of this pipe is actually 11 centimeters. So we are going to actually use that. And the velocity is 3 meters per second inside of this pipe. Here actually this is wrong. It says 10 centimeter pipe, but it is actually 11. So it should be a typo. And it discharges horizontally into the air at point C. So this is where we are discharging this water at point C. So to what height, h, above the water surface at A, can the water be raised if 28 kilowatt is delivered to the pump? So this means in this question, instead of calculating the power from pump, the power is actually given. So it is 28 kilowatts. And we are assuming that pump operates at 60% efficiency and the head loss in the pipe between A and C is equal to 2 Vc square over 2G. Again, we have a constant as 1 throughout the system. So again, let me write the energy equation. It's already given, but again, it is always wise to select between these 2 points, like between surfaces or at the outlet and the surface. So we have this energy equation. Turbine and head loss. So we are going to ignore some parts, like the pressure is 0, the velocity at point A is 0, and for the A, we can actually take it as the reference, so it is also going to be 0. But of course, we have HP, and on the right hand side, again, we have 0 pressure because it is discharging to the air, so that we have 0 pressure. But of course, we will have velocity because this water is discharged with a velocity. And we have ZC, so it will be this height between A and C. So we can call it H, because it is actually what we are going to find. And we don't have turbine, so it is 0, and we have head loss to V square over 2G. So if we modify, we have HP equal to 3 or H plus 3 Vc square over 2G. And the velocity is actually given as 3 meters per second. So since the pipe diameter is not changing throughout the system, of course, except this area, because it is just the suction pipe, then for the entire pipe from A to C, it is 11 centimeter diameter. So that this means we will have same velocity, same area, and same flow rate, because flow rate is Vc AC. So the water with 3 meters per second velocity is discharged through this point C as 3 meters per second again. So we have 3, and then we have area, which is pi times diameter square, which is 0.11 meters over 4. So it is 0.02851 cubic meter per second. So this is the flow rate within the system. And let's continue with the equation. So here we can actually calculate Vc square over 2g. So it will be 3 meter per second square over 2 times 9.11 meter per square second. So this gives 0.4587 meters. So currently we have almost everything to find the height. So let me continue from here. So as you know, the power equation for the pump is flow rate, specific height, specific weight, and pump head over efficiency. And here we actually need to find HP. So we can leave it alone. So HP is equal to P efficiency Q and specific weight. So we did that because the power of pump is already given as 28 kilowatts. So since we know the power here and we know flow rate, we know specific weight and efficiency, the only thing we don't know is HP. So that if we can find HP, then since we already know this term too, we can calculate this height. So let's continue with finding HP. So here we are going to use power as 28,000 watts because watt is Newton times meter per second, so that all terms will be in the same unit, like cubic meter per second, meters, and Newton per cubic meter. So we have 28,000. We have 0.6, which is for the efficiency. And we have the flow rate. And the specific weight. So this gives HP as 60.191 meters. And lastly, we can use this equation. Because right now HP is 60.191 meters equal to H plus 3 times 0.4587 meters, which comes from here. And finally, we can get H as 58 meters, 8 meters. This is question 3, 7.68. Here we have a system with 2 reservoirs, a device, and 2 pipes. So we need to find the flow direction, we need to find the machine at A, and we need to find out if these pipes have the same diameter. We are going to sketch an energy grade line, and we will find if there's a vacuum at any point. So first of all, we have hydraulic grade line here. So always the hydraulic grade line goes downward in the flow direction. So this means that we have downward from here. So this means this is the flow direction. And another proof is the hydraulic grade line is decreasing until here. Then we have a rise, and then we have another decrease. So here, the key point is that rise. So we have a machine here, and it should provide an increase in water height.
So this is most likely a pump. So pump should be assigned in the flow direction as well, so that we can say the flow is from right to left. And we also said it is pump. So let's see if these pipes have same diameter. So we have pump CA and pump AB. So here, as you can see from hydraulic grade line, this slope is less. We have smaller slope, but here in the section of pipe CA, we have steeper slope. So since hydraulic grade line shows the head loss in the system, steeper slope means higher head loss. And higher head loss means with the same flow rate, because the flow rate will not change throughout the system. With the same flow rate, smaller diameter means higher velocity. So when we have higher head loss, it means we have higher velocity. So to provide higher velocity, we need to have a smaller diameter in this pipe. So we can say that CA has smaller diameter. Now we are going to draw energy grade line. So a energy grade line is actually hydraulic grade line plus V2 square over 2G. So you probably remember from the course. So when we say energy grade line, it is actually V2 square over 2G plus P over gamma plus Z. So this part is hydraulic grade line, and the total is energy grade line. So that we should draw a line which is V square over 2G higher than the hydraulic grade line. So this is energy grade line, and as I mentioned, the distance between these two lines is V2 square over 2G. And lastly, it says if there's a vacuum at any point or region of the pipes. Vacuum means sub-atmospheric pressure or a pressure that drops below atmospheric pressure. So in the system, we cannot see anything related to this. So we will say no.
Okay, this is question for 7.71. We have hydraulic grade line and energy grade lines here. And we are asked to find which one is hydraulic grade line and which one is energy grade line. And we need to find if these pipes are the same size or which one is the smallest. Is there any region in the pipes where the pressure is below atmospheric pressure? What is the point of maximum pressure and minimum pressure? And we also need to find what is happening at point E, and if the pressure in the air in the tank above or below atmospheric pressure. And what do you think is located at point B? So let me get started with A. Here basically energy grade line is equal to hydraulic grade line plus V2 square over 2G. So this should be energy grade line and this should be hydraulic grade line. And in the second one, it asks which pipe is smaller or if they are same. So here we can actually say that the slope is steeper here. This means higher loss, higher friction loss. And higher friction loss comes from velocity inside of its equation. So it means higher velocity. And to get the higher velocity, we are going to use continuity equation. So since flow rate will be same throughout the system, and to get higher velocity, we need to have a lower area. So this means we need to have smaller diameter in pipe AB. Is there any region in the pipes where the pressure is below atmospheric pressure? So for that we can compare the hydraulic grade line and the pipe center line. So here, for example, at this point we have positive pressure. If they are at the same level, like this, then it means we have zero pressure. Or if they are lower than the center line, then it means we have minus pressure, or we have subatmospheric pressure. So this means from B to C, we have subatmospheric pressure. So where is the maximum pressure and the minimum pressure? Here we can actually say the bottom of the tank has maximum pressure. Because there's a static pressure here, we have pressure from the air. And at this point we will have pressure from air plus gamma h, which is specific weight times this depth. So it is highest at this point, and it is higher than the pressure in the pipe because the water is moving inside the pipe, so there will be some losses and it will not be static, so that the bottom of the tank has the highest pressure. In terms of the minimum pressure, it should be definitely between B and C. So this is because we said there will be minus pressure here. So from the hydraulic grade line, it is actually P over gamma plus the elevation. So normally, once we have lower elevation, it means we have higher pressure. And in this, for this situation, once we have a further hydraulic grade line or hydraulic grade line at a lower elevation, this means we will have a higher pressure. But since we have negative pressure, we will have the most negative pressure, or the smallest negative pressure. So that this point will be C. So this is pressure mean. So as I mentioned, when the hydraulic grade line and the pipe center line is at the same level, this means we will have zero pressure. So the question says that what is the location at the end of pipe at point E? So if you follow the hydraulic grade line, right now it is above the pipe center line, so it means we have positive pressure, but eventually it comes closer to this exit. So it comes closer to the pipe center line. It means it is approaching a zero pressure situation. So to get a zero pressure, it means we have an outflow from the system. So this might be outlet of the system. So we can say it is a nozzle outlet. G is the pressure in the air in the tank above or below atmospheric pressure. So it is actually above, because if it was open to the air, I mean the atmospheric pressure, it would be zero. But this time we have a additional pressure from the air, so it means we have above atmospheric pressure. So at point B, this can be abrupt expansion, because these expansions cause loss in the system. So we can say it can be an expansion, because as you can see, there's a decrease in the height of the grade line, so that it can be expansion considering the loss.
Okay, this is question 5, 7.74. Here we are assuming that head loss in the pipe system is given with this equation, and L is the length of the pipe and D is the diameter. So we need to determine the discharge of water through hydraulic grade line and energy grade line, find maximum pressure and minimum pressure location and values. So we can actually write energy equation between 1, which is the reservoir water surface, and 2, which is the outlet of the system. So let me write it here. Energy equation between 1 and 2. So we have this equation. We don't have any turbine or pump, so we have 0 HP and HD. And the pressure is also 0 because it is open to the air. And this is valid for both points. And V1 is also 0. We have Z1, which is elevation of 0.1, and it's given as 100 meters. We have V2 square, and we have Z2, which is 30 meters. And we also have head loss, as given in the question text. So if we modify this equation, we will get 100 meter is equal to, actually let me write here, 100 meter is equal to 30 meters plus V2 square over 2G. Plus head loss. So head loss is given 0.014 L over d v square over 2g. Here, the important point is this velocity and this velocity are actually different. This is because this velocity is coming from the energy equation, and this is the velocity just at the outlet of this pipe. So it will be V2. However, in this head loss, we also have another V, which is we have another velocity. So this means this is the head loss in this pipe, and since this is the head loss in the pipe, the velocity should be Vp, which is the velocity within the pipe. So that we are going to write Vp here. And after that, we need to find the relationship between V2 and Vp. So we can basically do that using continuity equation, because the flow rate will not change throughout the system. So entering flow will leave the pipe as it is. So the flow rate will be equal to V2 A2, and it is equal to Vp AP. So between these two equations, we don't know either of them, but V2 times pi 0.6 square over 4. So this is going to be 3. So area of this exit is 30 centimeters diameter, so that we are using 0.3. And for Vp, we have pi d square, and this time it is going to be 0.6 square over 4. It is 0.6 because we are dealing with conditions within the pipe, so it is given as 60 centimeters. And since we have same numbers, we can directly write V2 is equal to 4Vp. It is mainly coming because of if you divide 0.6 square by 0.3 square, then we will get this relationship. And now within the equation, we can actually modify the equation, and we can write 70 meters, which comes from this equation, is equal to V2 square. So instead of V2, we are going to write 4Vp square. So the square of 4Vp is 16 Vp square over 2g, plus we have 0.014. The L, which is the length, is 500 for the pipe. So we have 500. Diameter throughout the pipe is 0.6, and we are taking pipe's velocity. And now the only remaining is Vp. And from this equation, we can get Vp as 7.045 cubic meter per second. And now we can continue. We can actually solve A. So it says determine the discharge of water throughout the system. So since we already know the velocity and we already know the diameter, we can calculate flow rate using continuity equation. So we have 0.4 7.045 cubic meter per second times pi 0.6 square over 4. And this gives 1.99
cubic meter per second. And now we need to draw the hydraulic rate line and energy rate line. So as you know, the difference between hydraulic rate line and energy rate line is V2 square over 2G. So let me use red for the hydraulic rate line. So in this question, we don't have any pump or we don't have any other minor losses or turbine, so that we will have a constant friction loss. So this means the hydraulic rate line will decrease throughout the system. So we can actually draw something like this. And the difference between these two is V2 square over 2G. And this is going to be energy rate line, and this is hydraulic rate line. Okay. And next step is locating the point of maximum pressure and the minimum pressure. So to find the maximum pressure, we are going to benefit from hydraulic rate line. So if you remember, hydraulic rate line is elevation plus the pressure head. So once we have lower elevation, it means we will have higher pressure. The pressure is maximum at this point. And the next one is we need to find the location of the minimum pressure. So if you remember from previous questions, when we have a hydraulic rate line lower than the pipe center line, it means we have a subatmospheric pressure, or in other words, we have negative pressure. So this means that at this point we have negative pressure. So we could have a zero pressure at this surface. But since this is a subatmospheric pressure, or as I mentioned, hydraulic rate line is lower than the pipe center line, we have negative pressure. So this means that this point is minimum pressure point. So let's get back to calculations. Since we need to find the pressure at these locations, we need to write energy equation between this surface and this minimum point and this maximum pressure point. So I can actually write, let me say this is point A and let this point B. So first energy equation between 1 and A, which is minimum pressure point. So as always, we have P1 V1 square plus pump is equal to PA over gamma VA square over 2G plus ZA and head loss and turbine. But we don't have turbine, we don't have pump, and the pressure and velocity at point 1 is still 0. And this time, of course, we cannot say this is 0 because we have pressure. This is inside the pipe, and this will be P min. And actually, VA will be equal to velocity within the pipe. So we are also not changing that. So Z1 is 100 meters. we have P minimum or specific weight. This is normally 9810 Newton per cubic meter. But to stick to the solution, I'm going to also use 9800. Then we have Vp square over 2g. We have the A. So they have the same elevation, which is 100 meters. And the head loss is same, which is given in the equation, given in the question. So it was 0.014 L over D V square over 2G. So since we are dealing with this pipe, the length is given as 100 meter here. And the diameter is 60 centimeters. So we need to use these numbers. So we have 100 meter and 0.6 meters. Then we have pipe's velocity. Over 2g. So this is still Vp square over 2g. And from this equation, we can actually get P minimum as minus 82.6 kilopascal. And now we are going to apply the same equations, this time for maximum. So energy equation between 1 and B. So this is actually the maximum pressure point. We have same equation, which is energy equation. And this is P max. And this is again Vp square over 2g. So we are dealing with a point within this pipe. Still, this is the exit, but we are inside the pipe. So we need to use Vp, which is the velocity within the pipe, because this is not outlet, this is pipe's portion. And we have Z2 plus head loss. So these are again 0. We don't have pump. So Z1 is 100 meters. We will find P max plus we have velocity of pipe. Over 2g. The Z2, which is the elevation of that point, is 30 meters. Plus the head loss is 0.014 L over D. So we start from this surface and end at this point. So this means we have 100 meter here and 400 meter here. So we have 500 meter pipe. We have 0.6 and
again Vp square over 2g. So from this equation, P max will be 373 kilopascal. Okay, in question 6, which is 8.33, we have an oil with a kinematic viscosity and it flows through a smooth pipe with 15 centimeter in diameter at 3 meter per second. And what velocity should water have at 20 Celsius in a smooth pipe with 5 centimeter diameter to be dynamically similar? So the rule for fluids to be dynamically similar is when they have same Reynolds numbers. So let's say we have Reynolds water and we have Reynolds for oil. And Reynolds is actually equal to velocity times diameter over kinematic viscosity. So let's see what we have. We are going to find velocity here. We have diameter as 5 centimeters and we have kinematic viscosity, which is 10 to the power of minus 6. You can get this from tables in your textbook for 20 Celsius degree. So this is going to be equal oil's Reynolds number. So the velocity is 3 meter per second times the diameter is 15 centimeters and we have kinematic viscosity as 4 times 10 to the power of minus 6 square meter per second. So here the velocity of water will be equal to 3 meter per second times 15 centimeter over 5 centimeters and 10 to the power of minus 6 and then 4 times of that value. And from this equation we can get velocity of water as 2.25 meter per second. This is question 7, 8.34. So we have a large ventimeter and it is calibrated by means of a 1/10K model using the prototype liquid. So what is the discharge ratio QM over QP, which is model over prototype for dynamic similarity? If a pressure difference of 400 kilopascal is measured across ports in the model for a given discharge, what pressure difference will occur between similar ports in the prototype for dynamically similar conditions? So again, we need to satisfy that dynamically similar conditions. So we will have same Reynolds number for the model. So it will be same for the prototype as well. So let's get started. And Reynolds number is V velocity diameter over kinematic viscosity. So here, instead of calculating, instead of using D, we can also use L to represent the length or the dimension or the size, because both model and prototype are geometrically similar, so that we can directly use to make these calculations easier. You will better understand why I'm using L in next steps. So we have VM, LM. over viscosity. This will be equal. Same for prototype. If we leave this alone, we will have NP over LM and kinematic viscosity for model over prototype. So basically, we move this velocity here, LM to here, and viscosity to top. We only gathered same units here. So the reason for leaving this velocity rate or velocity proportion, because the question says there is a ratio for the discharge of model and prototype. So this means QM or QP is 1/10. Therefore, we are aiming to find QM within these Reynolds equations. Actually, let me move everything to up so that we will have more space. So to get Q in this equation, we need to multiply this V by area. So let me write area of model and area of prototype. So let's continue. So we will have VM, AM, VP, AP. This is equal to NP over LM. And now we will have area. So here we can actually say LM over LP square. So this basically represents area of M divided by area of P. This is because we took L as the main dimension. So the area of L will be L square. So it will not make any difference. For example, if you say we have a circular shape and we are using D as the dimension. So for example, you can say P square over 4. Let's say this is M. And PD square over 4 again. So here these will cancel each other out. And final output, again, same. dm square over dp square. So it doesn't matter if you are taking diameter within a circular shape or if you are taking length or L as your main dimension. So that here we are writing this in the form of LM square over LP square instead of AM over AP. And another thing here, since these are viscosity of the fluid, and since we are using same fluids in the model and prototype, then their viscosities will be equal to each other. So we can say this is actually 1. So we only have this equation. So let me continue. So as it is clear, we will have QM over QP, which is equal to LP over LM. Because we have LM square over LP square, so what we will have is LP over LM. LM over LP. So let's say this is the first equation. And in the second part of the question, this time we need to include the pressure difference because it is the other important information in this question to calculate the pressure difference in prototype. So we also have pressure coefficient, which is called Cp, or let me say Cm. And these pressure coefficients should be also equal to each other. So we will have Cm is equal to Cp. Or in your textbook, you can actually see Cp to represent pressure coefficient. This is equal to pressure coefficient of prototype. And the equation for this pressure coefficient is the difference in pressure over rho v square. And this is going to be equal to prototype's pressure coefficient. Again, we actually have same density because we are using same fluids for prototype and the model. So we will have pressure difference in prototype because it is what the question is asking. It will be equal to pressure difference in the model. And we have velocity ratio of prototype to model, and we are taking its square. And let me continue. And actually, I forgot to add, since we have this 1/10 scale in the model and prototype, Qm over Qp is equal to 1/10. And this is actually equal to Lm over Lp. So knowing that, we will continue the question. Pressure difference in the prototype will be equal to the ratio of length of model over prototype square because the velocity is length over second. So we can actually ignore second here. So what we will have is length because they will have same unit in the seconds. So what we will have is length. So basically from here we will get delta P, which is the pressure difference in the prototype, is equal to 400 kilopascal times Lm over Lp square. So from the first part of the equation, we actually calculated that Lm over Lp is equal to 1/10. So here we will have one 100. And from here we will get 4 kilopascal pressure difference in the prototype. We are at question 8 now. This is 8.60. We have a 1:25 scale model of a spillway, and we are testing it. The discharge in the model is 0.1 cubic meter per second. So to what prototype discharge does this correspond? And if it takes 1 minute for a particle to float from one point to another in the model, how long would it take a similar particle to traverse the corresponding path in the prototype? So if you look at your lecture notes and also textbook page 27, 275 and 276, and also lecture 17, page 16, you will see that if we are designing a spillway, then the model must equal to Freud number of the prototype. So this means Freud number of the model will be equal to Freud number of the prototype. And Freud number is velocity over gravitational acceleration times length. So let me start with this information. So we have Vm and we have same for the prototype. And here, of course, we can just ignore gravitational acceleration because it is the same anyway. So that from here, we can modify it in this shape. And then we can actually write these in meters per second form. So it means we will have length of prototype over time, and same for the model. The main reason to convert from this form to this form is we need to find the time so that we have time of model, because it says 1 minute to float from one point to another. So that we need to actually find TP, so that we are trying to leave TP alone in this Freud matching. So this is going to be equal to and from here we will get Tm over Tp is equal to so we have Lp coming here and we have Lm, and we also had Lp over Lm square root. So this means Tm over Tp is equal to square root of Lm over Lp. But since we need to find Tp, we can write this in this form, and it is going to give the square root of Lp over Lm. And let me continue from this side. So here Tp is Tm times Lp over Lm square root. So actually Tm was given as 1 minute. So we have 1 times, and we have 1 to 25 scale, which means Lm over Lp is equal to 1 to the 25. So it will actually give square root of 25. And from here, Tp is 5 minutes. So it means in the model, it takes 1 minute for that floating, and in the prototype, it takes 5 minutes. And we also need to find the prototype discharge. So let me continue from here. So if we consider these Freud numbers again, we can continue with that. So I can take the question from here. This is because we need to find the discharge, and here we already have velocity. So multiplying this velocity with the area, which will be L square, it will make our calculations easier. So let me apply what I'm talking. So we had Vp over Vm and P over Lm. And if we multiply this by area, we will have Qp over Qm. And this will be equal to Lp over Lm times Lp square over Lm square. So this is similar to previous question. So to calculate area, we actually just doing basic area calculation. And from here, Qp over Qm will be equal to Lp over Lm 5 to the 10, 5 to the 2. And here Qm was actually given as 0.1 cubic meter per second. And we already know the ratio of Lm over Lp, which was 1 to the 25. Then this is going to be 25. But of course, with the power of 5 over 2. So from here, Qp will be equal to 312 cubic meter per second. This is question 9, 8.8. Here, for very low velocities, it is known that the direct force Ft of a small sphere is a function solely of the velocity that passes a sphere, diameter d of the sphere, and the viscosity of the fluid. So we need to determine the pi groups involving these variables. So let me first find how many pi groups we have. So it will be n minus n. So here n means number of dimensional variables, and m means number of basic dimensions. So let me first find variables we have. So we have direct force will be function of velocity, diameter, and viscosity. So if you write all of them, I think from your lectures last slide, yes, you can find dimensions of these properties. So we have force. So it will be ml over t square. The second one is velocity. We have length over time. The other one is viscosity. We have m over lt. And last one is diameter, which is simply length or L. So as we see here, we have three basic dimensions, m, l, and t, which is valid for all of them. So we have 3, and regarding the variables, we have 4, so that eventually we will have 1, pi group. So if you follow lecture 17, lectures 18, you will find that we are using step-by-step method for Buckingham pi theorem so that we can determine the pi groups. So basically it starts with listing all variables, then eliminating dimension, which is L, then eliminating M, which is the force, and lastly, which is mass, and lastly we are going to eliminate the dimension of time. So let me write this. Our first aim is eliminating length, then mass and time. So we can focus here. So in the first variable, we write 1, 2, 3, 4. So in the first one, to eliminate m, we can actually divide it by diameter. So the main process is the use of variables here to eliminate L, M, and T, and lastly find the pi group. So here to eliminate L, we can actually use diameter because it already has the dimension of L. So it means if we divide drag force by diameter, we are going to get m over t square. And for the velocity, we can also do the same. V over t. So we will get 1 over t because we divided it by L. And for the viscosity, this time we are going to need to multiply it by L because we already have L here. So if we multiply it by L, we will get m over t. And lastly, since we use this variable, it already cancelled out so that we will not have anything to the final. So we are done with L. In the next step, if there is a mass in these variables, then we will need to eliminate mass. So to eliminate that, you can see we have m here and we have another m here. So we can actually use this variable so that it will be cancelled out, and we can also get rid of the m here. So let me do that. So we have ft and we need to divide it by dynamic viscosity times diameter. So we already have ft over d, and we divided it by viscosity times diameter, so that it is going to give, let me make a quick calculation. We have m over t squared, and we divide it by t over m over t, so it makes t over m, so that we will have 1 over t. And we have another 1 over t, and this is already cancelled out. So here we have same units, like 1 over t and 1 over t. So we can do either way. We can either divide this by v over d, or we can divide v over d by this variable. But to keep this at top, we can actually divide it by v over d. But the final group will be actually the same. So the only difference will be we can either find pi 1 or 1 over pi 1. So let's go with this one. So here we are dividing ft over t square by v over d. And this is going to give ft over d which gives ft viscosity d and 3. So this is the pi group from these calculations. So doing that, we actually applied also the last step, which is eliminating t. So let me put marks here. This is equation 8.10. Here we are considering a steady viscous flow through a small horizontal tube. For this type of flow, the pressure gradient along the tube, which is given as dp over dl, should be a function of the viscosity, the mean velocity, and the diameter. By dimensional analysis, derive a function relationship relating these variables. So this means we are going to apply a Buckingham pi theorem again, and we will apply step-by-step method. So this means the pressure gradient is the function of velocity, viscosity, and diameter, I guess. Yes, and diameter. So again, let's write everything here. We have viscosity, velocity, and diameter. So you can find dimensions. So for example, pressure is m over lt square, and we are dividing it by L. So this means we have m L square t square. For viscosity, again, we have m over lt. We have velocity of L over t, and lastly, again, we have L. And we will actually follow the same steps. Eliminate L, m, and finally t. So length, mass, and time. We are eliminating with this order. So let's first eliminate d for the first variable, which is pressure gradient. So we can actually multiply this by d square, because as you can see we have L square. So if we multiply it by d square, then we will get rid of L. So here we have m over t square. For the second one, again, we can multiply it by d, so or L, because L is the dimension of t. So here we will have m over t. For the velocity, we can divide it by d, so that we will have 1 over t, because we had L here. So if we divide it by d with dimension of L, then we will get 1 over t. And of course, this is already gone. So here the remaining is m. We need to eliminate m. So for example, in the first variable, we have m over t square. So if we use m over t, then we can get rid of m. So we need to divide this first variable with m over t. So basically it will be something like t over m. So we will get rid of m with following that. So this means we already had this variable, which is remaining from the first step. And then we divided by viscosity times diameter. So we are dividing it by this. Then what we have is delta P over delta A and D over nu viscosity. So this gives us 1 over T. This gives us 1 over T. So this means we got rid of this variable and we have 1 over D, V over D, which is 1 over T. Again, we can divide this by V over D. So we will get get rid of T. So we have this equation, and we are dividing it by V over D. It is going to give us delta P D square over delta L viscosity and velocity. And we got rid of that. And this is equal to constant C. So we had one pi group, and this is the pi group we have.